and reciprocal lattice. So lattice is like imaginary construct. Okay. So, and then for mathematical convenience, we are considering that we are converting the real lattice into reciprocal lattice. So that's what we saw in the previous classes. Okay. So today we are going to see the Bragg's law in reciprocal lattice. Okay. So already to have like a diffraction, we need to have like a Bragg's law. If it is not obeying the Bragg's law, we know that it is not going to give the diffraction. Okay. So we are thinking of like a reciprocal lattice. That means the reciprocal lattice also should satisfy the Bragg's law. Okay. So here there is a terminology called like a sphere of reflection, or otherwise called like a evolved sphere. So all those things, it is representing the same thing that we will learn today. Okay. So consider like a reciprocal lattice, and you have like a crystal somewhere here. Okay. So consider a reciprocal lattice. So you know the reciprocal lattice axis, which is like A star, B star, C star, all these things. Okay. So we are thinking of like A star, C star section through which an X-ray is passing. Okay. The reciprocal lattice where the section A star, C star, an X-ray is passing. Okay. Now, what I am considering this as an origin. Okay. At a distance of 1 by lambda. Okay. So at a distance of 1 by lambda, I am making a mark and making a mark which is called like a C, and keeping this as radius, I am making a circle. Okay. So from the point O, I am taking a distance of 1 by lambda, keeping it as a radius, I am making a circle. All right. So I'm calling it like this as like K naught. Okay. So then I am thinking of another point P, which is falling at the circle. Okay. So this is falling at a distance of 1 by DHKL. Okay. So since it is like a reciprocal lattice, okay. So at a distance like 1 by DHKL, okay, I am thinking of like another reciprocal point which I am calling as like P. Okay. So now I am making this as like a triangle OPD. Okay. So thinking like this is like making an angle of like a theta. All right. So since like a sine OBP, which is called like a sine theta, you can think of like sine theta is equal to OP divided by OB. Okay. So OP we know already is like a 1 by DHKL. Okay. So this OB is 2 by lambda because it is like 1 by lambda OC, and OB is 2 by lambda. So sine theta is equal to OP divided by 2 by lambda. Okay. So otherwise, I can say sine theta is equal to OP divided by 2 whole of theta. So since P is a reciprocal lattice point, because the length of like OP is like equal to 1 by DHKL, I can rewrite like sine theta is equal to 1 by lambda divided by 2DHKL, or I can rewrite. Okay, so this I can bring it here. So 1 lambda is equal to 2D sine theta. Okay, so we can see the Bragg's law even in reciprocal lattice. Okay, so now you think of like I told you this like an origin. Okay, this is like a reciprocal. This is like A star C star section. Okay, this is like a reciprocal lattice point. You have like a radius of like 1 by lambda. All right. So thinking that this, assume like you have like a reflecting plane here. Okay. So what will happen? You will have the diffracted beam just passing through this way, because you have the reflecting plane. So the diffracted beam will go like this, which will make an angle of theta. Right. So this will be the CP, that line connecting the CP should be parallel to OD. Alright? Okay. It is because like we are thinking like this, like a reciprocal lattice point. Okay. This is like 1 by lambda. Alright. So these two should be parallel. Okay. So crystal may be considered like centered either from here or from here. Okay. So if I thinking like CP is making CP is like a center, which is like making like more sense for following derivation. Okay. So the construction is not limited to A star C star section, but it holds for all the points on the circle produced by rotating the circle in above figure. Okay. So this figure illustrates this reciprocal lattice point, which is falling on like this circle. Okay. It is making a diffraction. Okay. Since it is making a diffraction, if I rotate the crystal, okay, so I will get like another diffracting, another point, lattice point, which will be falling somewhere here in the circle or somewhere here or somewhere here. Okay. So anywhere in the circle, whatever the spot. Okay. So by rotating the crystal, I can make all the points falling on this circle so that I can record all the diffracting points. Okay. So thus for any point on the surface of the sphere, the condition for Bragg law, Bragg reflection is fulfilled. Okay. So by rotating lattice about its origin, various reciprocal lattice points can be brought into coincidence with the surface of the sphere of reflection, and the corresponding reflection can be observed. Okay. So this is called like a sphere of reflection. Okay. Or you can call it like a evolved sphere. Okay. So if any reciprocal lattice point is falling on this sphere of reflection, then the reflection is recorded. Okay. So as I told you, here is the like a crystal. You can rotate the crystal. Okay. So here you are recording one reciprocal lattice point. If you rotate, maybe some other reciprocal lattice point may coincide with this circle, and hence you can record the reflection. Okay. So either you rotate the crystal or rotate the beam. So instead of sending the beam through this, I can send the beam like this. Okay. So the center will vary. So I can record some other reciprocal lattice point. Okay. So this is called like a sphere of reflection or evolved sphere. So changing the wavelength of the incident radiation has the effect of enlarging or shrinking the size of sphere of reflection. Okay. So this is a short lambda sphere. Okay. And this is longer lambda sphere. So by changing the wavelength, the size of the sphere of reflection will also vary. So thus every reciprocal lattice point within a sphere of radius. Okay, so this is like 1 by lambda. So the whole thing is like a 2 by lambda. Okay, so within the sphere of radius 2 by lambda, okay, the limiting sphere. So within like 2 by lambda, this is like a limiting sphere. Okay, so around this, like any like reciprocal lattice points is there. Okay, so think like if you rotate the crystal, so the sphere of reflection will rotate. So instead of coming here, it may go here, or it may make a circle like this, or it may make a circle something like this. Okay, so thus every reciprocal lattice point within the sphere of radius 2 by lambda, the limiting sphere is a potential reflection. And the total number of reflections possible for any molecule is limited to the number of reciprocal lattice points within the sphere. Okay. So within this sphere, you can find out the like number of reflection which is making like a which we are observing from reciprocal lattice. So, and the number of reflection for a molecule can be obtained from the number of reciprocal lattice points. So, if there is only one molecule per unit cell, the total number of possible reflections is equal to n is equal to 4 by 3 pi of 2 by lambda whole cube. So, this is, you know that. So, this is the volume of the sphere, okay, divided by volume of reciprocal cell. So, the number of reflection can be obtained by directly 33.5 into volume of direct cell divided by lambda cube. Okay. So, here you can think like you have the crystal, so you have the sphere of reflection or like evolved sphere, okay. So, wherever you have like a reciprocal lattice point which is falling on the this circle, evolved sphere, you can see here. So, it's marked like a red dot. So, these reflections will be recorded, okay. So, this red dot here, so this will be recorded. So, you see here, so many like lattice points are there, right? So you have like so many lattice points, but all the lattice points are not going to be recorded here. Why? If you going to record all these things, it will be a mess up, right? So only the reflections that is falling on the limiting sphere will be recorded. So you don't want to miss the other information, right? So that's why you will be rotating the crystal so that the origin and the place of the evolved sphere will be continuously rotating, so that it will be recording this point, the other points. All right, one by one. So by keep on rotating the crystal, all right. So you will be recording all the lattice points. All right. So when we rotate the crystal, reciprocal lattice also rotates. So more reciprocal lattice points intersect the evolved sphere of reflection is recorded. So the crystal is rotated about 1 degree or less. Okay, so I told you already, you will shoot the crystal at 0 degree, then rotate 1 degree. Okay, again shoot with X-ray, then rotate 2 degree, then again shoot with X-ray. So like that, one by one. So little by little, you will be keep on rotating the crystal, and you will be recording all the reciprocal lattice points. Okay. So as a result, okay, so you will have like a zero layer, zero order, and then first order, second order, so many reflections like which are, okay, this is a sphere, okay. Consider this is not a circle, this is a sphere. So maybe you can understand this in this picture. All right. So you see, this is like a 1 by lambda. Okay, this is the 1 by lambda radius of sphere. All right. So this is the zero order reflection, first order reflection, second order. All right. So I told you this is like a Debye cone. It's making like a cone kind of thing. Okay. So this is like first order cone, second order. So here you see, so all these points, whichever is not falling on the sphere, you see only the outer layer of this circle is supposed to fall on the sphere. Yes or no? So only these reflections will be recorded. So now if you rotate the crystal, so whatever the reflections already recorded, the position will be moving. So these inner reflections will fall into the sphere of reflection. So that makes to record all the possible crystal, the reciprocal lattice points. Okay. So you have like a cones of like diffracted X-rays from for rotating about a direct axis. So here you have like X-ray beam, you have the X-ray as a crystal. Okay. So one by one, so like all the like lattice points will be like recorded. Okay. So with this, I stop the sphere of reflection or like evolved sphere. So we are going into some like another topic, which is like the symmetry. Okay. Okay, so crystal system and the symmetry. So as I told you, crystal is like having like a symmetry. So what is mean by unit cell? It is the smallest repeating unit, right? So the same unit will be repeated n number of times throughout the crystal. So that means there is symmetry present in the crystal. So what is the advantage of having like symmetry? The advantage is, okay, if you want to calculate the entire structure, okay, the crystal lattice, okay, so if you have like a symmetry, you don't need to calculate for the entire section of the crystal. You can utilize the symmetrical information. So if I have symmetry and it will be sufficient to calculate only one portion of the crystal, because the rest of the portion can be generated by applying symmetry. Yes or no? If I know one half of the system, I can reproduce the other half of the system by means of like symmetry. By applying symmetrical operation, I can generate the other half of the system. So that is the advantage of the symmetry. Okay. So practically, how it does help? So practically, it will help you to reduce the timing of data collection. All right. So suppose your crystal is like a two-fold symmetry. So two-fold symmetry means assume like you are going to collect the data of 180 degree. Okay. So for your crystal, you have to collect for data for 180 degree. Okay. But the crystal is having like a two-fold symmetry. So you don't need to collect the data for entire 180 degree. Only just collect like 90 degree. Yes. One. Yeah. No. சரி எனக்கு இருக்காது மோடி சார் மோகன் சார் இல்லையா எஸ் சார் வரல எடுத்தது கால் பண்ணுங்க. So since like my crystal is having like a two-fold symmetry, I can collect the data only for 90 degree. All right. So you are collecting only for 90 degree. The remaining portion you can generate by applying symmetry. If my crystal is okay four-fold symmetry, right? So I can collect only like what 45 degree or what, right? Like six-fold symmetry, I can collect data only of 60 degree. So like that, the symmetry will be helpful for us. Okay, you can reduce the time of exposure, you can reduce the time of data collection. The calculation will be like very simple. All right. So that is the advantage of like symmetry. Okay. So in crystals, okay, there are like seven types of crystal system is there. So as I told you already, so we have observed only the crystal so far only within this 7 type of crystal system only. Okay. So assume like you have some curtain, something like this. All right. So what is this? Just like everything is like a symmetrically related. So this and this like 180 degree. Like symmetrical, right? So if I rotate 180 degree, I will get this one. And if I rotate this 180 degrees, so I will get this one. So if I am able to calculate, if I am able to find out the section only on this thing, all right? So the entire thing will be found applying by symmetry. So once I found the entire unit of this, I can reproduce the entire pattern just by applying symmetry, right? So that is the advantage. Okay. So we have like only 7 crystal system in this basically like in the crystallographic system. 5-fold symmetry is not possible. Okay, so like 2-fold, 3-fold, 4-fold, 6-fold symmetry is possible. Okay, but 5-fold is not possible. It's mathematically proven. But here, so what is mean by like 2-fold, 3-fold? So here you see here. So if you apply this symmetry, you will generate this. Then you will generate this. You will generate this. So completely without any gap, this pattern will be filled up. Yes or no? So without making any gap between these, right? So the pattern is like generated. So that is the applying. That is the meaning of applying symmetry. All right. So I am applying some symmetrical operation. I am generating this, but in the middle, if I have a gap, okay, so that doesn't make sense. All right. So when you apply like 5-fold symmetry, there will be some gap. There is no continuous packing. Okay, but it is surprising to see the tiles in the Alhambra Palace in Spain. So it is around like I think 9th century. How come they are making such a beautiful symmetry, which includes like a 5-fold symmetry and all other kinds of symmetry without like any gap? It is nicely packed. Okay, this is like a very quite surprising one. How they did, I don't know. So this is like a great puzzle. Hold on a second. Yes, sir. Yeah. So I want to get the signature from you. So how long you will be there, sir? I am taking class. I am in the middle of the class. Shall I finish and come to you? Yeah, I have given the file in the office. Just please go through. So meanwhile, I will finish the class and I'll come back. Okay, sir. Okay, thank you. ஹலோ இப்போ ஹெச்எட் இல்லை நீங்கள் அவர்கிட்ட கொடுத்துங்க. நான் இப்போ தான் அவர்கிட்ட பேசினேன். நீங்கள் கையெழுத்து வாங்கிடுங்க அவர்கிட்ட. நான் கிளாஸ் எடுத்துட்டு இருக்கேன். முடிச்சோன்னு நான் வந்துடுறேன். ஓகே. So it's quite surprising how come they did such a beautiful calculation. So some crystallographer even visited this place. And they saw this pattern and they made it like a paper also. Okay. So symmetry of the crystal is like a crystal system is like important and should be determined. So it reduces the number of unique parameters that must be determined while solving the structure. So crystals have like inherent symmetry. The definite ordered arrangement of the faces and edges of a crystal makes possible to correlate one part of the crystal to other part is known as crystal symmetry. So crystal possess different symmetries or symmetry elements. Okay. A symmetry operation is the one which leaves the molecule and its environment unchanged. It is an operation performed on an object or pattern which brings it to a position which is absolutely indistinguishable from the old position. Okay. So there are like 7 3-dimensional coordinate systems that are useful in describing system. Okay, so HKL are Miller indices, ABs are unit cell distances, alpha, beta, gamma are angles between the lattice directions. So these are like a unit cell parameters, okay, dependent on the symmetry of the crystal system. So here is the like 7 different types of crystal system: triclinic, monoclinic, orthorhombic, tetrahedral, rhombohedral, hexagonal, cubic. Okay, so triclinic, if you see, the number of independent parameters is 6, where A is not equal to B, not equal to C, alpha not equal to beta, not equal to gamma. So triclinic is the system, the cell, for which you need to collect data for entire 360-degree, because here none of the cell parameters is equal, it is unique. Okay, so only for this crystal you have to collect for entire 360-degree. So if you go to monoclinic, all right, so A is not equal to B, not equal to C, but alpha gamma is equal to 90-degree, beta is equal to 9, not equal to 90-degree. Okay, then orthorhombic, you can see A is not equal to B, not equal to C, alpha, beta, gamma is equal to 90-degree. All right, and then cubic, you can see A is equal to B, equal to C, and alpha, beta, gamma are same. All right, so depending upon the system, okay, the angle of data collection will vary. Okay, so for the monoclinic, you have to collect like a 90-degree. This orthorhombic, you have to collect like a 120-degree. For this, you can collect like a 90-degree. Rhombohedral, you can collect like a 90-degree, and so on. Okay, it depends upon the crystal system. So it actually reduces the number of cell parameters so that the calculation will be like very easy. So these are like the 7 crystal system. There are like the symmetry elements, and these are like 5 symmetry elements for which you will be operating. Okay, so proper axis, okay, proper axis of or rotation axis, it is indicated with like a N. Okay, so you will be rotating along 360 divided by N degree. Then another element, mirror plane or plane of symmetry, indicated with the letter M. If a plane exists in a structure, that every part on one side is related to the other part as by means of reflection. So center of symmetry, okay, indicated with like I. So inversion of all atoms through the center of the gravity. Improper axis of rotation, so it is indicated with the letter SN. So this symmetry will be having like 2 operation: rotation, okay, followed by reflection. You will rotate and then you will do the reflection. So identity element, it will do nothing, so it is indicated with E. So we will see the example, proper axis of rotation. So this is an axis passing through the crystal, such that if the crystal is rotated around, okay, around some angle, the crystal remains invariant. All right, so here you can see, so the axis through which you are rotating is like N4. Okay, so 360 divided by N. Okay, so that is the N4 axis. So I have to rotate this, okay, until I am getting what? Symmetrical thing. So this is 2-fold rotation, right? I have rotated, right? So initially I have a molecule here, so I am rotating this to get like a symmetrical one. So I have to rotate 180 degree. So here you can see this is a oval kind of shape. So this oval shape indicates 2-fold rotation, 180 degree that I have to rotate. Okay, so here, okay, so you can see it's a square. So this square indicates 4-fold symmetry. I have to rotate 90 degree. So rotate 90 degree, you will get this one. So you can call it like a C4-1. Rotate another 90, C4-2. Rotate another 90, C4-3. Rotate another 90, C4-4 or C4. Okay, which is identical. Okay, so here C4-1, you can say like a C4, and you rotate another C4, another 90 degree you will get here, right, which is C4-2 or equivalent to C2. C2 means 180 degree. You rotate 180 degree, you will get this one. So C4-2 is equivalent to C2. All right. So if equivalent configuration occurs after rotating 180, 120, and 90 degree, So the axis of rotation is known as like 2-fold, 3-fold, and 4-fold axis of symmetry. Okay. So if a cube is rotated through 90 degree about an axis to one of its faces at its midpoint, it brings the cube into self-coincident position. Okay. So this will be supposed to have like a tethered axis. Okay. So if n equal to 2, rotate through angle of like 180 degree. So it is called like a diode axis. N equal to 3, rotate 120, it's called like a triad axis. So n equal to 4, tetrad axis. N equal to 6, 60 degree, that is hexad axis. So far, as I told you already, 5-fold axis of symmetry so far is not observed, and mathematically it is proven there is no possibility of making like a 5-fold axis of symmetry. Okay, so we will prove that. So in the following section of this class. So here the symbol for 2-fold rotation oval shape, 3-fold triangle, 4-fold rotation like square, 6-fold like a hexagon shape, solid. Everything is solid. Okay, don't just put like a oval shape and line like a 2-fold. It should be a solid line. Okay. So then, so far we saw like an axis of rotation as a symmetry element. Now we are going for the plane of symmetry. Okay. So the plane of symmetry. Okay. So it is assumed to have like a mirror. Okay. So a crystal is said to have a plane of symmetry when it is divided by an imaginary plane into equal half. Okay, such that one is the mirror image of the other. Okay, so you can have like a 2 kinds of plane of symmetry. One is like a vertical plane of symmetry, and another is horizontal plane of symmetry. Okay, so if you take a cube, okay, so here I can have like a vertical plane of symmetry. Here I can have like a vertical plane of symmetry. It's a horizontal plane of symmetry. It's a diode. Okay, diode passing through the corner. Okay, it's a diode. Okay, so along through the diagonal, right? So that is also a symmetry. Okay, then center of symmetry. So it is a point such that any line drawn through it will meet the surface of the crystal at equal distance on either side. Okay, so I am starting from here, passing through the center, and I am reaching the same point at the opposite direction. If I have like a same molecule, that's called like a center of symmetry. Okay, so for example, I can tell you like easily like carbon dioxide, right? So you can have like oxygen here, like a double bond, carbon, and double bond oxygen. So I start from here, passing through the center. This is I, and I am traveling at the opposite direction, reaching oxygen again. So this carbon is center of symmetry. Okay. So symmetrical elements of a cube. So in cube you can see like a center of elementary. Center of symmetry is 1. So planes of symmetry, 9 planes of symmetry. You have like a diode axis, tetrad axis, and so on. Okay. So then improper axis of rotation. So improper axis of rotation, I told you, you need to have like a 2 kinds of operation together. Rotation followed by inversion. So if any molecule is having like this both operation together, then the molecule is said to have improper axis of rotation. Okay. So assume like you have a molecule like this. All right. So what I will do is I have to first what? Rotate. Okay. So I will rotate this. Okay. So this, if I rotate like a 90 degree, this will come here. But you can see this will be facing on top only. Right? So I have completed only rotation. Now what I have to do? Inversion. Right? So if I invert this, right, I will get this molecule. Okay. So if I have any molecule, okay, having related by means of rotation followed by inversion or followed by reflection. So then it is said to possess what? Improper axis of rotation. Right? Okay, so is the time now? Alright, so still have some more time. So I told you there is no five-fold symmetry. So we have seen earlier that the crystalline solids show only like 1, 2, 3, 4 and 6-fold axis of symmetry and not 5-fold axis of symmetry, or higher than like 6-fold axis. Okay, so the reason is that a crystal is one in which the atoms or molecules are internally arranged in a very regular and periodic fashion in 3-dimensional pattern. An identical repetition of like a unit cell, it can make only that can take place only when we consider these 1, 2, 3, 4 and 6-fold axis. Okay, so if I think of like 5-fold or like 7-fold, higher order, 8-fold or a higher fold of axis, okay, it's not possible for to have like a proper geometric arrangement. So think of this 5-fold object. Okay, if you try to pack, how will you do the packing? So you can put another molecule here, right? Then I have to pack like another molecule, something like this. So internally you will have a gap, right? So or else, if I pack something like this, right? So here, then again, there will be a gap, all right? So you think of, you try with like higher order, so there will be a gap. But in the crystal, it is not possible to have a empty space. Okay, so that's why it is not possible to have like a 5-fold, 6, 7-fold, 8-fold or higher order. If you construct a model of like a 6-fold, try with like 6-fold, you will be having like a proper packing of 6-fold system. You will not have like any gaps, right? So you can see like continuously it is packing. So here also, right? Sorry, so it is gone back. Okay, so this has to come something. Maybe I can try here, right? Yeah. So in the 6-fold, you will be having like a continuous packing without any gap, right? But in case of these 5-fold or like any higher order, it's not possible, all right? So you can think of like different packing. So whatever you try this way, or you want to put here, so something that some gap will be there, right? So yeah, so I have it shown here, right? You can put here, or you will put here, whatever you do, then definitely you will have some gap over this region. Okay. So mathematically, how can we prove it? So let us consider a lattice PQRS. So as shown here, so assume like you have like a lattice PQRS, okay, with a distance of a parameter, okay. Let this lattice has n-fold axis of symmetry and the lattice parameter be equal to a. So let us rotate the vectors QP and RS through an angle theta, which is equal to 360 divided by n, in the clockwise and anti-clockwise direction respectively. Okay, so in the clockwise or in anti-clockwise, you rotate to an angle of theta. So after rotation, the ends of the vectors be at x and y. So consider this as like x and y. So since the lattice PQRS has n-fold axis of symmetry, the points x and y should be the lattice points. So further, the line xy should be parallel to the line P2RS. So therefore, the distance xy must be equal to some integral multiple of the lattice parameter A. Okay. So we can say it is like a MA. So that is xy is equal to A plus 2A cos theta, which is equal to MA. So here M is equal to 0 plus or minus 1 plus or minus 2 plus or minus 3 and so on. So from this equation 2A cos theta is equal to MA minus A, or like 2A cos theta is equal to A of M minus 1, or cos theta is equal to M minus 1 divided by 2, okay, which is equal to N. Okay, so here N we know 0 plus or minus 1 plus or minus 2 and so on. So since M minus 1 is also in integer, say N, so we can determine the value of theta which are allowed in a lattice by solving equation 2 for all the values of N. Okay, so for example, if N is equal to 0, cos theta is equal to 0, that is theta will be 90 degree. So that represents N equal to 4-fold symmetry. In a similar way, we can get like 4 more rotation axes for N equal to 1, N equal to 2, N equal to 3, and N equal to 6. Okay, since the allowed values of cos theta have the limits between like minus 1 to plus 1, the solution of the equation 2, okay, the solution of the equation are not possible for N is greater than 2. So therefore, 1, 2, 3, 4 and 6-fold axis can exist. So here you can see, like, so if I put line like N equal to 1, that is like 360 degree. N equal to 2, that will say that you will get the equation of the solution at like 180. So N equal to 3 means 120. N equal to 4 means 90. 6 means 60. So try with like 5, you will not get these values. Alright. So you try to pack like in any way, but that's not going to work. Okay. So I have like explained you the symmetrical elements. Okay. 5 types of symmetrical elements, that is like proper axis of rotation, plane of symmetry, center of symmetry, and improper axis of rotation, and identity element. Okay, so with this I stop here. There is another symmetrical operations as well. Okay, so here you are applying like only one type of symmetry, either reflection or rotation, or like reflection and rotation followed by, right? So there is another kind of symmetrical operations in which you will be doing like a translation as well. Okay, so maybe I will take that part in the next class. So who is taking next class today? Students? Okay, so afternoon? Afternoon, no free classes, huh? Okay. Okay, so anyway, so we will see tomorrow, all right? So with this I will stop.